Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled PLD Implementation Exercise, Entering a Truth Table in VHDL, Behavioral Approach. I can't believe it, but we're going back to the Happy Cat cat food factory. We're going to do another PLD implementation exercise. And this lecture kind of serves two purposes. Number one, we're going to use the techniques that we just learned in this particular unit to develop the minimum SOP expression. Okay, in the previous time we visited the Happy Cat cat food factory, I just gave you the expression. Now what we're going to do is we're going to pretend that we are their production manager and we're going to develop the logical expression. How did he get that in the first place? Part two of this lecture is we're actually going to show you how VHDL can implement an expression for you. And that's kind of known as the behavioral approach. And I can't believe I'm showing you guys behavioral approach before structural. We've been kind of and we'll go into the differences between them, but that's the way it happens. Behavioral approach is basically you're telling VHDL to do something and it implements it for you in its most efficient method. There are people that think the Kmap is dead, that think that SOP minimization is dead, that think that an understanding of Boolean laws is dead because VHDL does it for you. I'm here to tell you they are incredibly far from the truth, because you will see, I know VHDL can do it, but look at the amount of time it takes to do it, and compare and contrast. You will end up the same results. But if you have the skills that I'm showing here for Kmap minimization, coming up with a minimum SOP expression, you can pretty much breeze through this thing, okay? Whereas behavioral approach, sometimes you gotta really lay it out and write a lot. It is up to your personal preference, however. It really will implement the same expression. Let's go back to the Happy Cat cat food factory, and again, I know that you have the minimum SOP expression from our previous examples, but what we're going to do is we're going to pretend that we don't have that, and we're going to try to develop a truth table. Basic problem statement. There are 3 inputs and 1 output. What is the output? Well, the output is cat food, okay? It is the constituents of the cat food. It must have 1 source of protein and at least 1 filler agent. Corn husks are a filler agent. Gym mats are a filler agent. Seals are a source of protein. Just on that problem statement alone, you should be able to figure out a truth table, okay? What are my inputs? Seals, husks, and mats. What's my output? Cat food. I'm going to go ahead and signify that I've got an acceptable form of cat food when I get a 1 at the out. Come up with all possible combinations of input, and the next step, think about it. Fill out the truth table. Go ahead and try it, and pause the lecture. Go ahead and see if you can come up and stay in this orientation. Seals, husks, mats, that way we're all on the same page. Go ahead and fill out that truth table. I'm going to go ahead and pause the lecture and see what my estimate of it is. There you go. How did I get it? Well, let's do an intermediary steps. Okay, remember what I said earlier is you could put notes off to the side. Think about it. There are no seals, there are no husks, there are no mats, there's no inputs. There's nothing to make it. Cats cannot live on air alone. What about the second occurrence, 0, 0, 1? Okay, it's just filler. 0. Again, 0, 1, 0. It's just corn husks. It's just filler. 0. What's the next one? Seals, no seals, husks and mats. 2 types of filler, no protein. 0. Okay, you can make these notes. Your notes might be different than mine. What it's just describing to you. 1, 0, 0. Just protein. 0. Aha! What's this one? We got seals and gym mats. Don't know if you noticed that. It's even got blood stains on it. 1. Good to go. We got seals and husks. 1. Finally, the happiest cat ever. Seals, husks, and mats. 1. This notes, I know it may seem kind of dumb to you. That is going to describe to you how that truth table works. Use those notes if it helps you. Don't use them if you don't. I've come up with the truth table. What's my next step? Put it in a Kmap. Put it in a Kmap and come up with the minimum SOP expression. So what's my bare Kmap look like? Looks like this. Okay, there's my bare Kmap. How am I going to organize it? I'm going to put S and H on this side, M on that side, because again, I'm following the order of the truth table. Following the order of the truth table. You can do it backwards. It's going to be hard. Okay, and now what I'm going to do is go ahead and 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Put it in the truth table. Okay, I'm looking for an SOP expression. All I need to worry about is the 1s. These guys right here. Put in 1, 0, 1. There's a 1. 1, 1, 0. Put in a 1. 1, 1, 1. put in a 1. There you go. Now, what's the next step? Group it. Triangular group of 3 or right angle group of 3? No, that doesn't exist. There's a group of 2. There's a group of 2. What's the next step? Come up with the product expression for the term in red. Come up for the product expression for the term in blue. And once you've done that, sum them together to get the result, cat food. It's a sum of that product and that product. Okay, go ahead and see if you can come up with the product term for the one in red and for the one in blue. What I'm getting is something like this. There you go. Seals and husks or seals and mats. Last step. Does it make sense? Does seals and husks satisfy the original problem state? It needs one source of protein and at least one filler. It certainly does. Does seals and mats? It certainly does. It makes sense. Have that sanity check. And I know we did this really slow, but I mean, how long did it take me to do this? Maybe, I don't know, 3 minutes? What I'm saying is that 3-minute investment to do a minimum SOP expression and then write up in VHDL, you can do that. You have the skills to do that. And we already did that in a PLD implementation exercise. You can come up with a minimum SOP expression and write this out really quickly in VHDL. And now compare and contrast to what I'm going to talk about is the behavioral approach. Okay, the behavioral approach. I've already kind of written what I want to do. I've got an entity. What is it? It's called HappyCat2. So I've started the entity HappyCat2 is, bookend it with end HappyCat2 semicolon. Okay, what's in between? I've got my input ports. I've got 3 input ports. These guys right here, the same ones we had before, because there's 3 ins. This time though, I've got 2 outputs. What I'm going to do is I'm going to call it a cat food SOP out. And then I'm going to have another output, cat food behavioral out. Okay, what I'm going to try to do is show you, I'm going to come up with 2 expressions. And they should be the same. Cat food SOP, that's exactly what we just came up with. Seals and husks or seals and mats. Cat food behavioral, once I show you some of these, the select statement, you will see that it will implement the exact same output as cat food SOP. However, you're going to have to put a little bit more effort into it than our 3-minute SOP expression, our minimum SOP expression. I got a blank architecture statement, a big old blank architecture statement, because I want to set this thing up to do, let's do the simplest one first. I mean, let's just come up with the expression for cat food SOP output. And you should know this one. This is the exact same one we did in our last PLD implementation exercise. And by the way, it's the last one we just came up with right here. So just write cat food SOP output in good VHDL syntax. And again, we're using seals actually spelled out, husks actually spelled out, and mats actually spelled out. Okay, so go ahead and see if you can write it. And where are we going to write it? I would probably write it in here. Okay, go ahead and give it a shot. And there you go. Cat food SOP is assigned parentheses seals and husks or parentheses, or excuse me, close parentheses or parentheses seals and mats parentheses semicolon. Okay, by the way, over here is architecture. I'm calling it SOP versus behavioral of HappyCat2 is because basically what I'm going to do is now come up with the expression for cat food BEH, cat food behavioral. It takes a little bit of setting up to do this. To use what I'm going to call the select assignment or a with select statement, which is kind of a behavioral approach to this, I've got to set things up in a vector. Notice my inputs are standard logic. My outputs are standard logic. I've got to kind of put them in a vector format. Okay, I've already declared them as standard logic. How do I make them a vector? What's cool is notice how I put some space here? What I can do is actually declare an internal signal. Okay, what is that section there? That's the declaration where I can use an internal signal. And what I'm going to do is I'm going to make that internal signal a vector. And then once I'm in my begin portion of my architecture, I can actually assign these inputs to that vector. Okay, I know this why am I doing this? But check it out. I'm setting up this select statement. Okay, so let's go ahead and declare an internal signal, and it's going to be a standard logic vector. Let's call it SHM, since we know and we want to keep that orientation. Seals, husks, mats, and geez, I can't just write SHM. That's going to be bad. I got to write signal. I got to tell in this declaration that it's a signal. Let's call it SHM. So signal SHM colon, what is it? It's going to be a standard logic vector. And it's kind of like that, the port assignment, but I don't need to declare it as an input and output, remember, because it's something internal to my architecture. Okay, so I'm going to call it standard logic vector. Okay, what's the size of this guy? Okay, it's 3 because it's got seals, husks, and mats. And what I'm going to do is I'm going to say assign it an MSB and an LSB. So what's my MSB? I could call it 3 down to 1, or I could do 2 down to 0. Either way, it's 3 elements, and that's ultimately what I want to do. I want to have 3 elements. So I'm going to say 2 down to 0. Close it up with a semicolon. Okay, so all I've done right there is declared an internal signal that I can use, and how I'm going to use it as a vector. Okay, now I've got to do something with that signal. Maybe what I could do is potentially assign seals to the MSB, i.e. SHM2, SHM1, SHM0. Okay, so how do we do that within the architecture statement? Well, it's pretty simple. It's kind of just like that assignment. All I'm doing is this, I'm going to say SHM parentheses 2 assign. What am I going to assign? Seals, semicolon, SHM1, husks, SHM0, mats. Pretty cool, huh? And this is, again, we're just setting it up. We had to declare, we had to move those things in there. We had to declare an internal signal and move those things in there. Now we could start using our behavioral approach. This is a neat thing that VHDL can do, and it takes a while to implement it. What you basically do is you tell VHDL with this vector input, with that particular combination, spit out this output. With this particular combination, spit out the next output. And you're basically just telling it what your truth table is. So what you got to do is you have a good understanding what your truth table is, and you're going to put in when it's 000, spit out a 0. When it's 001, spit out a 0. So on and so forth. How many times am I going to have to do that? 8 times. This is why I'm saying, no, the Kmap is not dead. 3 minutes effort at most. I came up with that. 2 seconds of writing effort. I wrote the VHDL expression for this. I know that I could do the behavioral model where I'm doing the select assignment, but I've got to do it 8 times. Add another variable to that. 16 times. Add another variable to that. 32 times. You get my picture? However, it's still going to implement the same results. And the other thing is notice who I've assigned first. SHM2, that's seals. SHM1, that's husks. SHM0, that's mats. If I said 001, what I mean is this, and not that. Critical to staying organized when you're writing these select statements. Okay, let's go ahead and write the general formula, general format for these select assignments. So the first thing is you want to say with what? With SHM. Notice I'm not telling it 2, 1, or 0. I'm saying the whole vector. Select. What am I going to select? Well, I'm going to select from my truth table, but what I'm assigning to is my output. What's my output? Well, it's that one. Since I've already done cat food SOP, what I want to do is cat food BEH. And notice how I'm kind of giving myself a little bit of indent there. I'm telling myself, hey, I'm inside this with that particular input. Select. I'm within here, and structurally I can see, okay, I'm in that assignment, and I could potentially write some other code below it. Okay, what do I want as my outputs? For the first one, just do it from top to bottom. I want to output 0, okay? Assign a standard logic element. Notice the single quotes, because what is my output? It's a standard logic. It's not a vector. So assign it a logical 0. When, what is my input? It's SHM, which is a vector. Double quote, double quote. Okay, so that's my input combination. What is my input combination? Reading from seals, husks, mats, staying in MSB to LSB order. It becomes critical because you cannot assign these things backwards. Your truth table won't work. Well, it's 000. Notice the double quotation marks for vector usage. There you go. You got your first assignment. So with SHM, select. Here's my first one. Cat food is assigned a logic. It's going to be standard logic 0 when the vector element SHM is equal to 000. Double quotation marks. Notice I'm commaing it. What do I do for the next element in the truth table? Well, you don't really have to do this again, because this comma statement means I can keep on writing. Okay, so I'm going to assign it on. What's my next element in my truth table? 001 should give me an output of 0. So output 0 when 001, comma, keep on going. Do you see what I'm saying? You got to do this 8 times. Go ahead and see if you can write the up to 7, up to 111, and it's going to look something like this. And I'm going to do something at the very end that's kind of cunning here. You'll see. Okay, there you go. And I don't know if you guys caught this. I should have. What is the actual name of my output? It's okay. So I'm trying to do is compare and contrast, and I don't know what happened to the formatting there. Kind of compare and contrast the behavioral versus the SOP implementation. Notice I got the comma of it every single line. So if you think about this, what I'm doing is 000, 1, 2, 3, 4, 5, 6, 7. I've gotten to 7. You think that I'd close the whole thing up because that's all possible combinations, right? I can't get anything else. And what else am I missing? These should all be vectors. I'm telling it that whole string. And again, what's the MSB? The one on the left. What's the LSB? The one on the right. How have I defined it? MSB to LSB this way. One would think that I could just put a semicolon right there, right? Close up the whole thing. But check this out. It's good practice. Comma. Continue with one more statement. And this is pretty cool. Others. When others. It's one of those cases that I know I've been talking about zeros and ones being the only acceptable binary values. There are things that are unknown or uninitialized or indeterminate logical levels. So say for example there is one of the sensors for these things is not giving a clear 0 or 1. How do you want your output to respond? Others. Basically it's saying that that whole grab bag, there's a bunch. Yeah, I know I've been just talking about zeros and ones. There are a bunch of different types of variables that you can come across in VHDL, and we'll talk about those a little bit later. But for right now, there's others out there that I haven't talked about. U, Z, X. And you've seen a couple of those U's in the simulation program. Okay, how do I want this thing to respond when others? Do I want to potentially get the FDA on me? Or I don't know if the FDA bothers with cat food. But when I signify that, hey, that's an acceptable form of sustenance for our beloved cats. You know, maybe from the, if it's an unknown situation, maybe I want to say 0. Maybe there's some troubleshooting I need to do. I could potentially get in a problem if I'm saying no sensor input, i.e. there's no input there. I'm just saying, yeah, that's great, that's great, that's great. I don't recommend that. 0. So this is a pretty neat walkthrough right here of our first kind of behavioral approach. What is this output right here going to look like? Exactly like that output. What do you think it's gonna do? It's gonna do that for us. Because check it out, we came up with a minimum expression right here. We did 3 minutes of work versus 9 statements. Yeah, if you don't want to put the effort in, if you don't want to use minimum SOP expressions, if you totally forget how a Kmap works, yeah, you could use this behavioral. The thing is, you got to write some more. The SOP minimum expression Kmaps, they are not dead. VHDL has not superseded these. An understanding of the basic principles behind digital electronics will save you a lot of effort. Okay, last but not least, let's close up our architecture, because that's, again, we're bookending between beginning all the way down to end. And then when we run our simulation, the cat food SOP, cat food behavioral, through its magic with this select statement here, should output the same values, okay? Just in a different form. Or just in a different method of getting there. Okay, so that's what I'm talking about. The data flow versus the behavioral. There are more than one way to feed a cat. Okay, so I am currently in the ISC Project Navigator Webpack for Xilinx software, and this is a PLD implementation environment. And again, this VHDL program, which I've written right here, should be portable as long as it fits on the particular device that I'm trying to fit it onto. All I've done is I've written the VHDL program, which we had previously written in OneNote. What are the 3 elements of a VHDL program? Library up here, entity, defining the inputs and outputs of it, architecture, defining how it behaves. What have I done initially? I've got a declaration, an internal signal, which I'm calling SHM. All I'm doing is I'm making use of internal signal, which is a standard logic vector. Why am I doing this? I'm setting it up so I can use this select statement later on. Begin. What I'm going to do, this is not the best VHDL program. Why? Because I don't know what I'm doing. I have no comments. What I can do is type in a comment. the double hyphen there. What I'm saying is this is the SOP implementation that I came up with on such and such date. And now what am I doing? Assigning standard logic inputs into vector so I can use it with the select statement. So I'm basically giving myself little breadcrumbs when I come back to look at this thing later on. Now, what am I doing? I'm within that select statement right here. This is the select statement output. Compare with SOP output. Ideally, they should be the same. Additionally, notice this will output 0 if other input, an uninitialized or a high impedance or an unknown state. That's probably a pretty good idea when you're dealing with manufacturing of some potentially poisonous substance, okay? All right, so here we go. This is our VHDL program, basically exactly what we just wrote there, just in that environment. Let's go ahead and try to do a simulation on this thing. And again, that's the radio button that will kill you. I'm going to go ahead and click on it. I want to simulate the behavioral model. Run. Save the changes, yes, because I put those comments in there. It's running the simulation. I'm going to go ahead and pause, and we're going to come back up into iSim. Okay, here we are in iSim. Notice the difference already. Cat food SOP versus cat food behavioral. Look at cat food behavioral. It has a 0 output. Why? Because of the other statement. Because of the other statement, because our unknown inputs, we haven't assigned them anything, it's outputting a 0. Pretty cool, huh? What is this thing right here? Okay, that's the vector SHM. It's an internal signal. So that's what's really cool about these simulation programs. I do get access to those things. I actually can see those internal signals on the simulation program. If I was to hardwire this thing, I know that I've directly assigned seals, husks, and mats, but let's say those were internal things that I couldn't access. I can visualize them, okay? Alright, so let's go ahead and force a clock on this one. Seals, force clock. What I'm going to do is I'm going to say leading edge 0, 1. Let's go for 16 microseconds. I feel like I'm doing this thing all the time. 60 microseconds. Apply. What's the next one? Husks. Okay, so far seals was our MSB. Our next one down should go twice as fast. Apply. Mats. And again, apply. Let's run our simulation for 16 microseconds. Zoom into where I'm at. Look at seals. It's a bunch of zeros. Then a 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Notice my SHM vector. This is pretty cool. 000, 0, 0, 1, 0, 1, 0. It's telling me from MSB down to LSB what that is. Okay, it's giving me the state of my truth table because it's a vector. I can also open that thing up and it's seeing, okay, mats is assigned to SHM0, husks is assigned to SHM1. It's pretty cool. You can see these vector values. Notice, however, there are unknown inputs prior to the start of our simulation. It takes a little bit of time to set this thing up, so there are unknown inputs there. So there's an unknown output for an SOP expression at that initial onset when there are unknowns. But look about that cat food behavioral. There is a known output there because it's others. That's the power of that other statement. What's the gist of this whole thing is, look, besides this little glitch at the beginning, look at cat food SOP, look at behavioral. They're performing the exact same logic function, strictly by magic. It's not magic. Our cat food SOP, we came up with that expression using a Carnot map. We came up with a minimized expression in 3 minutes. We wrote the cat food behavioral description with a select statement in maybe 8 minutes, the 8 entries, but check it out, they're still doing the same things. Strictly through optimized software, it came up with the exact same expression that we came up with, which is ultimately what we want. So this has been a super quick description and implementation of a PLD using all the techniques we've learned thus far in Unit 5. And I've showed you an additional step in entering a truth table in VHDL. Okay, this concludes this portion of the lecture.